Alright, so today we're diving into the world of carboxylic acids and exploring the variety of reactions they can undergo. Carboxylic acids are incredibly versatile molecules in organic chemistry, serving as starting points for synthesizing numerous other compounds. In this video, we'll cover how carboxylic acids are made, their common reactions, and some fascinating applications like saponification. By the end, you'll have a solid understanding of the fundamental transformations involving carboxylic acids. Let's get started. Carboxylic acids can be synthesized through the oxidation of primary alcohols or aldehydes. This is typically done using a strong oxidizing agent like potassium permanganate or KMnO4. Here's how it works. When a primary alcohol is exposed to an oxidizing agent, it first forms an aldehyde. If oxidation continues, the aldehyde is further oxidized to form a carboxylic acid. This transformation is critical in organic synthesis, providing a pathway to create carboxylic acids from simpler organic molecules. Next up, we have nucleophilic acyl substitution, one of the most common reactions involving carboxylic acids. This reaction is characterized by a nucleophile attacking the electrophilic carbonyl carbon of the carboxylic acid, which leads to the formation of a tetrahedral intermediate. Here's how it unfolds. The nucleophile approaches and attacks the carbonyl carbon, which temporarily breaks the carbonyl's double bond, forming a tetrahedral intermediate. Next, the carbonyl reforms, pushing out a leaving group in the process. This reaction is versatile and can produce several different compounds depending on the nucleophile involved. If the nucleophile is ammonia or an amine, the product is an amide. Amides are named with the suffix amide. When amides are cyclic, they're called lactams. If the nucleophile is an alcohol, the product is an ester. Esters are named using the suffix O8. Cyclic esters are known as lactones. If the nucleophile is another carboxylic acid, the product is an anhydride. Anhydrides can be linear or cyclic and are named with the suffix anhydride. Each of these reactions expands the versatility of carboxylic acids in synthetic organic chemistry, allowing for the creation of various functional groups and complex molecules. Carboxylic acids can also be reduced to primary alcohols. This requires a strong reducing agent, such as lithium aluminum hydride, or LiAlH4. During the reduction process, the carboxylic acid first forms an aldehyde intermediate, which is then further reduced to a primary alcohol. It's important to note that while LiAlH4 is strong enough to carry out this reduction, sodium borohydride, or NaBH4, is not. NaBH4 is a milder reducing agent commonly used in organic chemistry, but lacks the strength needed to reduce carboxylic acids. This distinction is crucial when selecting the appropriate reagent for your synthetic pathway, especially in more complex organic syntheses. Another interesting reaction is decarboxylation, where carboxylic acids lose a carbon dioxide molecule. This typically occurs in beta-dicarboxylic acids and other beta-keto acids when they are heated. The reaction proceeds via a 6-membered cyclic intermediate and results in the loss of a carbon atom as carbon dioxide. This reaction is quite valuable in biochemistry and synthetic organic chemistry, especially when modifying or shortening carbon chains. One of the more everyday applications of carboxylic acids is saponification. This is the process of forming soap by mixing long-chain carboxylic acids, often called fatty acids, with a strong base. The reaction produces a carboxylate salt, or soap. Soap molecules have a hydrophilic, or water-attracting head, and a hydrophobic, or water-repelling tail. When placed in water, these molecules organize into structures called micelles. The hydrophobic tails face inward, trapping nonpolar substances like grease and oil, while the hydrophilic heads face outward, allowing the micelle to be washed away with water. This dual nature of soaps is why they are so effective at cleaning, dissolving both water-soluble and fat-soluble substances. Alright, so to sum up, carboxylic acids are not just simple organic compounds, but versatile intermediates in many chemical reactions. From nucleophilic acyl substitution creating amides, esters, and anhydrides, to their reduction into primary alcohols, decarboxylation for removing carbon atoms, and even their role in saponification to make soaps, carboxylic acids are truly multifunctional. Understanding these reactions is essential for anyone delving into organic chemistry, whether in academic research or practical applications like medicine and industrial chemistry. If you found this video helpful, please give it a thumbs up, share it with your friends, and don't forget to subscribe for more in-depth chemistry content. And if you're using the King of the Curve app or web app, leave a like there and comment on what topics you'd like us to cover next. Check out the app for even more in-depth content. Thanks for watching, and see you in the next video.